I want to thank the organizers for inviting me to this very special workshop. So in this 30-minute talk, I'm going to talk about some the experimental observations of spin current effects in 2D magnetic systems, and I would just focus on two representative layered materials in this family. Okay, so just a brief outline. So I'm going to briefly mention this van der Waals spin heterostructures. And in fact, in my talk, I'm going to just talk about so-called half van der Waals spin structures, because I'm going to just mention this half of, okay, so this heterostructure here. So iron germanium telluride with heavy metal as a platinum. This is the platinum on top. And the other one is somewhat called inverted structure with a platinum under. I'm going to tell you why. So under chromium triode layered magnet. Okay, so we have a small subset of 2D family that the members are magnetic. So the properties vary from, quite a bit, ranging from insulator to metal to semiconductors. And also there can be ferromagnetic, antiferromagnetic, or even quantum spin liquid and quantum anomalous Hall. So there are a lot of interesting properties and attract a lot of research in the field. So I will just focus on, as I mentioned, this iron germanium telluride. So I will call FGT from this point, although FGT could be other closely related compound with more iron content, but here I specifically refer to 312, right? Iron 3. Germanium 1, tellurium 2, and the other one is the chromium triode. Okay, so first of all, the 2D van der Waals heterostructure can be in principle made with the aid of automated transfer station put inside a glove box to protect samples from oxidation. So by doing this, we can extend the lifetime of the device, especially with some of the air and moisture sensitive materials in the material stack. So with that, we can make a variety of heterostructures composed of the members of the van der Waals family that I showed earlier. The magnetic ones. Okay, so the attributes of the van der Waals heterostructure in general include their atomically, you can build it really atomically flat. Flat is sort of a morphology, but actually atomically sharp from chemical point of view. There's no diffusion, interdiffusion, mixing. Okay, as opposed to the materials grown by at high temperature. So this, because we're not using high temperature process, this can be done with relatively low temperature, which diffusion is greatly suppressed. Okay, then there's, you imagine, you can mix and match all different materials to create a larger number of heterostructures. Okay, so in the process of the transfer, we can, using this material in glove box, this is just one example that showing that how much one can do. So with this boronite, actually we have this fuel graphene as a bottom gate, and then separated from your channel by this boronitride, this bottom layer. And then we can pick a single layer or multi-layer WT2 Then on top of that, we can put any 2D magnet, in this case, chrome triodide, this a working device actually. So then on the very top, we can put another layer of boron nitride to sort of seal off to protect this whole active device from exposing to air or moisture. Okay, so this is my sort of outline now. So the second part, I'm going to focus on this half heterostructure, the van der Waals heterostructure. So I picked FGT for studying the spin orbital torque. So I want to tell you the motivation on this slide. So as I mentioned earlier, so the interface can be atomically sharp and flat that originates from the surface, atomic layer, the surface. Okay, so this greatly suppresses spin disorder. So the scattering can be suppressed, both spin-dependent scattering or diffuse scattering. So that actually is, in general, I would argue that this is very good for spin orbital torque. Then second is among other magnetic layered materials, this FGT has so far the highest Curie temperature. This one is for 312 compound, right? The Curie temperature is about 225 K or so. So better than other 2D magnets from application point of view. So the this is a very unusual property. The FGT has a very strong perpendicular magnetic anisotropy. That comes from actually monolayer, this monolayer unit. So the anisotropy at the low temperatures, lowest temperature, we can calculate, actually agree with the theoretical prediction, they calculated to be larger than 10 to 7th erg per centimeter cube. So this is a very, very strong considering just the one monolayer, and you can compare with a three-dimensional ferromagnetic material. This is a really strong anisotropy. So by itself, this is the mechanism. It's very interesting. But this is for application, especially for memory application. This is very desired property. So the high resistivity for spin orbital torque purpose, the high resistivity in this layer, the magnetic layer is desired because we want to use the other metal layer to create a spin current. We don't want to have a current shunting effect. So the last one, in order to achieve a low critical switching current, this low saturation magnetization also helps. So low magnetization, but a strong perpendicular anisotropy. Okay, so we start off with this single crystal, a little piece single crystal, not large, but it's sufficiently large for exfoliation. So it has a very well-oriented single crystal. And in general, we exfoliate it and we isolate it. We just make, because it's a metallic, right? We can directly put electrodes on. Actually, FGT is not so air sensitive. If we do things really, I mean, it degrades slowly, but if we do things quickly, we can still make a really good device. And this is, in general, this resistivity versus temperature. This arrow points to the TC, the Curie temperature of this device, just FGT alone. Okay, so the anomalous Hall, you see this FGT shows beautiful anomalous Hall loops down to 2K. So this TC should be around here. From sort of arrow plot, we know the TC is actually 225 or so. Okay, 225K is the TC as mentioned, and the 2K at 2K, this course of field is about 7.5 kilorostat as you see here. I want to point out that for the experiments I'm going to show you, we done the spin orbital torque experiment measurements at 180K. So at 180K, the loop is shown here. the corrosive field is 10 times smaller compared to 2K, but it's still okay, this much, but it's about compared to the anisotropy at a same temperature, which is a 3 Tesla. So you see this, there's a 40 times difference between the corrosive field and the anisotropy field. Okay. All right. So now I use a set of the 3 slides showing the quickly showing the fabrication process for CGT, which is another layered material, but this similar process. I just simply use this. Okay. So first we isolate a piece. Okay. Isolate piece, then put electrodes. In this case, gold, platinum. And we use sputtering to create electrodes. Then we do. We have a thin film platinum everywhere. Okay, later on serve as electrodes. Then put a gold. Those especially this color, gold color. This is gold electrodes. Then we mask off the regions that we don't want to be etched, including the channel and electrodes, Hall electrodes. And then we etch away the rest, then to preserve this Hall bar shape. So this, in the end, this is the photo of a real device, but it's a CGT. So we have a longitudinal leads and the transverse leads for Hall measurements. So we use almost exactly the same processes for FGT. As I mentioned, FGT actually is a little more resistive to oxidation and in air. Okay, so here I show this interlayer, inter-unit atomic layer unit. So the distance is about 16 angstroms, right? So before deposition, this is a typical piece of FGT. So we see the RMS roughness is barely about 2 angstroms, okay? 2 angstroms after a 5 nanometer platinum deposition on top, is essentially the same. The roughness is about slightly increased, but it's still about a 2 angstrom roughness. So this 2 angstrom compared to 16 angstrom interlayer the unit, we don't see any atomic steps. So we don't see any extra or deficit of the atomic layer, okay? So on the surface. So we claim this surface actually of FGT is atomically flat in the sense of we have no missing atomic layer or extra layer anywhere on the surface. So so this is a slightly okay. This is a device that I made with this is different. This device has a platinum on top. So in order to switch the magnetization from the perpendicular direction up to down, so we use this spin orbital torque, this field-like torque together with this bias field we call HX, H not here, along the X direction. Then these two makes the switching deterministic. So this relevant, the field corresponding to the damping-like torque is shown here. Okay, so to set up the pulse current switch measurements, I want to show this is a sort of hard access loop. So by sweeping the implant field, HX, so switching implant field because of the slight tilt, right? So there's a switching. Then we set up for every switching event, we set up initial state here, either here or there. Then we apply current pulses with right polarity. So we want to switch from here to the other direction. So the pulse width is about half microsecond to avoid the heating. So we switch every current we switch, then we capture this the current dependence, the amplitude dependence. So these are the anomalous Hall step. So after applying current pulses, So with a different easy access field, I mean, not hard access field in the plan. Okay, so basically, so we plot all the data showing here. So we extrapolate using this equation here to extract the 0. This should be HX, the implant field, either here or there. We get this JC at a 0 implant field is around 2 by 10 to the 11 amp per meter squared. Okay, so so in principle, if we had a single domain switching, we use this equation, we could estimate, we could calculate this the spin Hall angle or the spin over torque efficiency. But as I mentioned earlier, so at 180K, even low temperature is the same, right? So we have enormous anisotropy field compared to the corrosive field. So this is definitely not a single domain. The switching actually is done by multi-domains. So this equation cannot be strictly used. So from this critical current, we can get some parameter here, but this should not be this exactly the spin over torque efficiency. But nevertheless, we listed this efficiency here because of a very small corrosive field compared to the anisotropy field. We get inflated this parameter here, but it still compared very favorably with other materials. Okay, so in order to get a better the spin over torque efficiency from the sort of single domain regime, so that we can get this sort of the figure of merit to compare with other experiments. Right? We do this second harmonic Hall measurements. From this equation here, we can extract the spin over torque efficiency from the various plots here. For different here I only show the two current amplitude. So now we can calculate this spin over torque efficiency. I listed here how FGT was a platinum. So by comparing with a 3D metal or 3D insulator with a platinum layer. So this is sort of fair comparison. So platinum layer, so this actually stands, the number here, spin over torque efficiency stands very well in comparison with other 3D metal. Okay, so I just want to point out that the 2D ferromagnet showing very high spin over torque in the first batch of devices with not optimized materials or processes. We get this much efficiency, so indicates a great potential for 2D ferromagnets. The reason I like to advocate is this atomic layer flatness and sharpness of the interface. So that is the reason I think for this high spin over torque efficiency. So in the remaining time, I like to talk about the other structure, inverted structure. We have a platinum under the chrome triide layer. Okay, so everybody knows this for the thin film regime. If you get down to a few layers, we see this oscillation between layers in the coupling, right? Single layers, you have a ferro, then you have an anti-ferromagnetic coupling between two layers. And the question is, but if you compare to the bulk hysteresis behavior, the chrome triide does not have sort of the same anti-ferromagnetic type of a loop like this, right? So that means there's some coexistence, indicates some coexistence between the ferro and anti-ferromagnetic phases. So the question is, how thick is this anti-ferromagnetic coupled layer in any stack, right? Any film, thin film, or flakes. So then another question to ask is why there should be a anti-ferromagnetic. That's a little more harder question. Okay, so in order to understand that, we use a low temperature magnetic force microscopy to study flake. This is flake also under a protection of platinum, the same process for the electron measurement. So this piece is a flake of chrome triodide. So we perform the experiments at a 10K. So with 5 Tesla, we have a relatively uniform contrast. This a dark a very bright line. Probably it's a geometric. There's a defect. Okay, the step maybe some step between these two parts. Okay, so when we decrease the field, we see especially around 2 Tesla or so, we see a lot of small regions with contrast, right? The regions show up, and we go for the decrease. We see these regions actually change contrast, and until even very low, very close to 0, so 0 Tesla, we still see the domain contrast. Okay, but a very faint, right? So here, so going to a negative, very faint. Okay, so notice that the MFM tip itself is magnetic. It also switch. The switching occurs at a very small field, like compared to this field range. Tesla range is like a few hundred Ørsted. So we do this line scan, okay, repeatedly scan in the same place across the edge. We can establish a reference point outside this. Okay, in this figure here, showing left is FGT. Chrome triodide. The outside is the reference, which is just a substrate. So we sweep magnetic field in this axis, the vertical axis, so we can actually average to get the response in MFM. So we see this phase shift, the response here. If I rotate it by 90 degrees, is this plot here. So we see that something happened at 2 Tesla also. Okay, remember this is MFM. We detect the straight effectively the straight field second order derivative. Okay, straight magnetic field, which is related to moment. So some moment abruptly switch at 2 Tesla also. Then keep at low field. There's a lot of switching, a lot of moments. And remember here the other side. Okay, the other side should be the tip is already flipped. So if we plot the moment correctly, the moment should keep going. Then it's anti-symmetric around the field. Okay, so the history on this side 2 Tesla also, we should also have a step. So now it's plotted here, right? This 2 Tesla jump is more or less symmetric against the field. So this is definitely antiferromagnetic coupling, right? Antiferromagnetic, some switching happened. So it's not a ferro because it happens from on the same side. If we sweep down, then same side already switched. Okay, so in order to know how thick, roughly estimate how thick the surface layer, so we exfoliated several pieces with different film thickness, the flake thickness. So we can estimate from the total thickness, total signal, we estimate this the jump, the magnitude of the jump, which is proportional to the thickness of the surface layer that antiferromagnetic coupled. So we, from different thickness, we see down to 25, almost like every, this all jump is due to this surface layer, right? So we plot the thickness dependence. We know this roughly the surface layer antiferromagnetic coupled thickness, it remains about 24 nanometers also. So if you think both surface can have this layer, so each side is around 10 to 12 nanometer also, that's antiferromagnetic coupled, right? So basically we have a simple model showing that the surface layer is sort of monoclinic phase here, showing here, which is preserved from the high temperature phase. High temperature phase, we know that's a monoclinic, okay? So this is a simple model we learned based on the fact that we learned from MFM measurements. So we do transport measurements because chrome triodide is very insulating, especially below 60 K or so, the ferromagnetic transition temperature. So we use platinum as a proximity sensor. Okay, so the reason we have an inverted structure with platinum below is because chrome triodide is very moisture sensitive. So we do this pre-patterned platinum first. So showing here. Then we introduce the platinum. Platinum is very robust, right? You can make them, you can do whatever with it. It was introduced after we introduce into glove box. Then we do everything, exfoliation, everything inside. We don't expose this air, sensitive layer. After we cover this layer by another boron nitride, then we can bring this this device with the boron nitride, bring out to do transfer measurements. Okay, so let me go a little faster. So this is the layer with platinum magnetoresistance as we sweep perpendicular magnetic field. So with chrome triodide above the platinum. Okay, this is the layer with a platinum only. So you see this shape is overall is similar to this background shape in this first device with chrome triodide. So in addition, we pick up some jumps, the jump roughly around 2 Tesla or so. In addition, the jump, okay, so there followed actually immediately after jump, there's also a tail, right? That's a kind of a rotation. So, okay, we put them together, we have this additional feature due to chrome triodide. Okay, so if we do a subtraction, so we see this, okay, overlay this two, we do subtraction. So I only show the positive side here. So we see 3 regions here, right? So this jump, I want to point out that this jump, right after jump, there's a gradual change in the magnetoresistance. It finished almost like around 8 Tesla also. Okay, from 2 Tesla to 8 Tesla. Okay, so these 2 features, the jump and this gradual change, these 2 features cannot be simply explained by spin flip of antiferromagnetic, one of the anti-coupled layer switch, right? For one reason is that 180-degree switch, the magnetoresistance cannot sense unless there's some unusual unidirectional MR involved, right? Which we don't think so in this case. And second, there's if there's a spin flip transition, then after the transition, after the jump, the magnetization is already locked along the applied field direction, then there shouldn't be any gradual change. So from this 2, we think this is the spin flop transition due to the antiferromagnetic coupled interface layer, because platinum only senses the surface layer or layers of the 2D magnet. So we think this region 2 is this spin, so it's called spin flopped state. Then rotation, I mean, region 2 is after the flop, then there's a rotation, right? So then fully spin aligned state is at this high field. Okay, so this is the spin flop critical field, which depends on the exchange field and anisotropy, the competition between the 2. If the anisotropy is small compared to exchange, then we have a spin flop. If anisotropy is larger, then the spin flip would be preferred, right? So we can trace out this temperature dependence, the spin flop temperature dependence. It disappeared around 45 K or so. We believe that this is the case when the spin flop, the critical field is 0. That means the exchange coupling is about equal to the comparable to anisotropy field. Okay, so this is a slide, last slide with the data. So when we do this the probing current dependence from very small current, even below 0.5, we did that also, then increase the current. If we do that with a fixed system temperature, right? We set the system temperature, same temperature, then we have a very different behavior. Okay, the reason is when we increase the current to some level, the sample start to heat. Then at some current, the real temperature will exceed, the sample real temperature will exceed the Curie temperature. So we'll see this loop, I mean the jump will disappear, although this system temperature we set at 2K, for example, but high current, this jump will disappear at a high current. But here we managed to set the sample temperature to be exactly at 25K. So at every current, we adjust the sample, adjust the cooling rate. The sample temperature is adjusted. I'm sorry, the system temperature is adjusted so that we keep the sample temperature at 25K. So how do we know it's 25? We measure this platinum resistance. So to keep the sample temperature, right, exactly at the same temperature. So in this case, we only see the current effect, not the Joule heating effect, right? So in other words, the other effects due to the current than Joule heating, we see this rise of this around 2 Tesla or so, the jump rise from above zero. Okay, so we compare this same temperature, the behavior of the current dependence. We see there's some minimum critical current is needed to see this feature, and we see the larger current, the larger the jump size, which is probably due to the angle, right? Spin flop, the intermediate, the angle. Then the large angle will give you, due to the angle argument I showed you earlier. So this, we look at this, we propose some model. This probably is due to this spin orbital torque. Again, the spin current effect through the spin orbital torque. In this case, basically you torque both layer magnetization so that it tries to push it over to this spin flop state. So we don't have a quantitative analysis. So it's somewhat like a reduction of the anisotropy from its behavior, like anisotropy due to this spin orbital torque. So relatively speaking, you have a lower anisotropy so that we can trigger this spin flop transition due to this competition between exchange and anisotropy. Okay, let me summarize my talk. In the first part, I show you the switching use of pulse current. We demonstrated a very low low current density for this FGT platinum. Is low 10 to 11 amperes per meter square. And if we do spin orbital torque efficiency measurements, the efficiency is comparable with the highest available data shown in three-dimensional ferromagnet with a platinum layer. Okay, so I'm not mentioning other layers such as a TI or gold platinum, but just to compare with the platinum, this is among the highest spin orbital torque efficiency. So both are, as I mentioned earlier, I think it's due to this the atomic layer flatness of the interface. In the second part, I mentioned there's an antiferromagnetic coupled surface layer. So we believe that's due to the coexistence of the monoclinic phase with respect to the bulk rhombohedral phase, which shows at low temperature shows ferromagnetic property with a very low switching field. And the induced magnetic resistance can faithfully reflect the spin states on the surface of a chrome triadi. And from the MR jump, and we can probe this spin flop transition and its current dependence. So we think it's a spin orbital torque induced anisotropy reduction, but this needs to be more investigated quantitatively. Okay, so in general, I like to end with the optimistic note that with the 2D van der Waals magnetic material, along with 2D other material to form van der Waals heterostructure, have a great potential from a spintronic perspective. Okay, finally, I'd like to thank my collaborators and thank you for your attention. I'll be happy to take questions.